Okay, let's look at second order rate dependence. In order to obtain a linear relationship, you have to plot 1 over t versus time, and so the integrated rate law turns out to be in this form. 1 over the concentration of t would be equal to y. You understand that we have y equals mx plus b, where in this case y is 1 over the concentration of A at a given time, and then k is going to be equal to the slope here. X is t, or time, and then the intercept b here, and this is equal to, so b would be equal to 1 over the initial concentration of A, right? And then of course you're provided with this information. You just have to determine occasionally if this is second order. You have to be told in order to use a correct equation. We also will do some problems with half-life, and here it's not a constant. It's actually dependent on the concentration, so it's slightly different. The math is not all that complicated here. And as we know of already that K has units, you can look at the units and know that what order a particular reaction is. So that's also sometimes a dead giveaway. Let's take a look at an actual example. So what we normally collect in the laboratory is data, concentration of a particular reagent versus time. That we can do. And once we have that, if you plot that, right, the concentration of, in this case, let's say it's NO2, that's our only reactant. It's a decomposition here versus time, and so if you plot that and it's linear, we know it's zero order, and then we know the mathematics become pretty easy. We already have a linear relationship. But for second and first order, you're going to see a curve like this. You cannot tell by what order it is for first or second order. You have to plot. You have to just play around with it. So you can use Excel for that, and we will look at that in a minute. So here we see a plot. Those are the black spots, the black data points here. We see the plot of time versus the natural log of NO2, which if that was linear, it would be first order. But as you can see, that's not linear here. It's also curved, so it's most likely second order. And just to confirm that, you now have to plot 1 over the concentration of NO2 at a given time. And then if that's linear, we have second order rate dependence, or dependence on the concentration of nitrogen dioxide. So here is that plot, and that's definitely linear. And you can determine the equation, the intercept here, and so here, as we said, the slope is going to be equal to k, and that's the graph is linear. The slope is equal to k, so here's k, and since we have the actual equation, we also know what 1 over A at the initial concentration, that's your intercept. That's going to be plus 100. So you can determine the concentration after 2,000 seconds by using this information, just plugging it into that integrated rate law, right? So we're gonna do, and this is example 14.5. We're gonna determine the concentration of NO2 after 2,000 seconds. If we had the initial concentration, we could just plug it into the integrated rate law, but since that's not provided, we actually have to use this equation and solve for y this way, right? And so we'll just say that y equals to 0.255, and that's k here, and I'm going to put the units in per molal per second times x, which is t, or 2,000 seconds, plus 100. And so if I solve for y, I get 610 per molal. And from the integrated rate law, I know that 1 over y, not 1 over y, but that y is equal to 1 over the concentration, in this case of NO2, at 2000 seconds. So now I solve for NO2 at 2000 seconds, and that's just simply going to be 1 over 610 per mol. And so what I get for that is 1.64 times 10 to the minus 3 molar. So that's the answer to this question. That is the concentration after 2000 seconds. All right, just a summary here. Again, the equation here, y equals mx plus b, or y equals k times time plus intercept, is represented by this integrated rate law. This is for second order. I'll write this. This is only for second order. Okay. And so now we're going to look at an example. Oh, not yet. We're going to look at zero order, which is mentioned multiple times before. That's the easiest one. If you have a zero order, that means the concentration is completely, the rate is independent of the concentration of your reagent. And so the rate simply becomes K here. The rate's equal to K. And then therefore the concentration of A versus time is linear, and then the slope is equal to negative K, and so our integrated rate law is simply the concentration at time t equals to negative KT plus the initial concentration. So very, very simple, not really worth mentioning. Okay, so now we're going to use Excel and plot this data ourselves, right? So the tabulated data shows the concentration of cyclobutane versus time. So this is just A going to B. The reaction is shown over here, and what we're measuring is time versus concentration. Just looking at that, you cannot determine anything whether it's first, second, third order, fourth order. It does exist, but we'll stop at 2, of course. So what you want to do is you want to just simply take this data and put it into Excel, and then plot time versus the concentration. If that's linear, it's first order. Sorry, 0, 0, 0, 0. If you plot time versus the natural log of A, and we can do all these calculations in Excel. You don't have to do that. It does it automatically. It's a very useful tool. If that's linear, it's first order, and then time versus the natural log. Sorry, it's going to be 1 over t. We just did that, right? And if that's linear, it's second order. So let's go to Excel. So I've got the data here, and so before I plot, what I want to do is put in the code for these calculations. So we're going to do equal to ln, and then highlight your concentration like that. So the code is here. Equal is going to be a mathematical function, and then ln, capital L, capital N, and then what do you want to do the natural log of? This is here, the cell B2. I hit enter, and then there are a couple ways to do this. You can just highlight, and it'll do all those calculations. We can start plotting that now if we wanted to, but let's do this first. We're going to do equals 1 divided by that cell. That's pretty simple. Oops. And also wait for the little x. So that's our data, and now we're gonna plot. Now after I've calculated all of my data, now I can start plotting. So the first thing I want to check for is first order. So I'm going to highlight the data, hit insert, select the scatter plot. Okay, I want XY because I don't want. I want to click on that, and here we have the correct data, which is you can make it pretty. You can give it labels. This is seconds here. This is in concentration or molarity. You can see this is not linear, so it's not zero order. what you can do is you can then right click and change that, and just simply select and remove the data, and then add the data, and you can just highlight what you want to add. So this would be X series. Oops, no, that's not what I want. Down here is the X series, so this is what you want to highlight for X. And then erases equals brackets parentheses 1, and highlight the second data here, which is the natural log of A. Then you click A, OK, and look at that. We have a linear relationship. We now know this is first order. You right click and you can add a trend line, and you can display the R value, you can display the equation, and so this is how we obtain the data for that. The R value is perfect here. R squared is equal to 1, so this is really good fit. If you were to go back and do a trend line on the other data, time versus concentration, you would not get as good a data. Or R value, you would get an R value that's less than 1. Just for kicks here, let's change this and select the data. I'm going to remove all of it. I'm going to add, again, I want a series name. I can give it a series name, call it a second order, and then I highlight, I want time, and it likes to do equals to 1. Erase that, select the 1 over t, which is for second order, hit OK, and you can already see that it's not linear here. If you do add a trend line and display the R value, it's actually not bad, but it's not 1, so it's 0.976, and you can just visually see it's definitely not linear. So once we've done that, and here I have everything actually nicely where I didn't override anything. I labeled everything so you can make your data look just as beautiful. I expect you to do that for the lab. Right? You can label your axes, you can call it first order, second order, display the equation. But the point of this exercise was for us to determine that we have a first order reaction and to get the equation here. And once we have the equation, I'm going to go back to PowerPoint now, not the Washington Post. So we know that rate, oh nice, it's red, rate equals to K times the concentration 0.25 m. We know this is first power. We know what K is from the equation. I know that K is equal to 0.0112 per second, and the concentration is 0.25 moles, and that gives me a rate of 0.0028 moles per second. Okay, again, that's actually here. And before I go to half-life, that'll be my last lecture. I'm going to take another nap. Thank you.